All right, so we have our plane that we're looking for. Oh, it's a smallish vector. Yeah, not as nice as it was. I thought it was. All right, so I want to know what this vector is, or I want to find a representation of this vector, but since it's really, what we're really concerned about is really the direction. It doesn't have to be a unit vector. It doesn't have to be, the length of the vector is not important. I'm more concerned about the direction. So here's what we're going to do to find this vector. I'm going to say, what if I want to run, rise over run is what I'm getting at. If I want to run along the y-axis by 1 unit, then I can say that this vector would be a 1 unit in the y direction. How many units will it change in the x direction? Why?
Because you're just running along the y thing. You're saying x
You're not coming along, you're not coming off of the YZ plane, so you're not moving in the x direction at all. So this is a vector with no movement in the x direction. And now I've established a movement in the y direction of 1 unit. Then how can you tell its movement in the z direction? Close. F of 0, no, not close, sorry. Good guess. I need more room. Rise over run. I said the run was going to be the 1, A1. The run was going to be 1, so what's the rise? In this case, it's going down, but think about it as rise anyways. How'd you figure that? Close. So that, I think that's the same reason Maria gave, but it's not quite that. But it is Fy. But not at 0, 1, because 0, 1, the thing that you put into Fy is a point.
X naught, Y naught.
So we want it x naught, y naught, not 0, 1. Okay? So x naught, y naught tells you, this, in fact, was what we said to be the slope. Right? And the slope is rise over run. So if we force the run to be 1, then the rise is going to be that itself, the slope itself. So this vector here is a vector tangent to the surface going along the y direction. Let's call it Vy. Okay? So remember, no movement in the x, so that's 0 in the x. And then for the y and the z, it's the rise over run. The rise over run has to match the slope. The slope is m, or the slope is Fy, evaluate x naught, y naught. So if we force the run to be equal to 1, then the rise would be the slope itself, Fy. Okay? All right, we're going to do the same drawing. Where we make our cut along the y equals y naught plane. And then we have this curve similarly. That is on the plane y is equal to y naught. That's parallel to the xz plane. And then we would want to find the slope of that like we did before. And the slope here would be, this time the x moves, the y is fixed. So we're going to take the derivative with respect to x at x naught, y naught. And then we see the same rise over run business where y is fixed this time. We run along the x by 1, and so our rise is going to be your slope. So we'll call it Vx equals, we're running along the x by 1 unit. We're fixing y so we don't move, so there's 0 movement in the y. And then the rise is Fx. Okay. So what we've then found is this vector that is also tangent to the surface. So we have two vectors that are tangent to the surface, so you could probably be certain that those two vectors are on the tangent plane. And you know that when we have two vectors that are on the tangent plane, we can find a vector that's perpendicular to that, and that's going to be our normal vector to the plane. And how do we find a vector perpendicular to two other vectors? We cross them. So we'll call this n for the normal vector. This is normal to the surface, and we'll cross them. Now, I suppose it doesn't really matter which one goes first, right? So for now, let's put Vx first, and if we switch them, you know that it's just going to be negative. So let's take the cross product of those two vectors. You got the I, J, K. The Vx is 1, 0, Fx. The Vy is 0, 1, Fy. And when we cross them, the first component is going to be 0 minus Fx. The second component would be negative Fy minus 0. And then the third component will be 1. Yeah, there was a little X in there, I just couldn't see it. So that's your normal vector. So if you have a vector that's perpendicular to the plane, oh wait, do we have a point on the plane? X naught, Y naught, Z naught. What's Z naught equal to? So that's z naught, f of x naught, y naught. So we do have a point on the plane. We have a normal vector to the plane. So we should be able to find the equation of the plane. So what's the equation of the plane? The equation of the plane, let's rewrite our point here. So our equation of the plane is the normal times x, right? So it'll be minus fx x naught y naught, which is just a number eventually, times x wait, how's the equation of the plane go? X minus x naught? Plus minus fy, x naught, y naught, y minus y naught, plus 1 times z minus z naught equals 0. Yeah? Oh, this? Yeah, let's put that there. So according to the formula that Alex and Renee put up last time, I think z was by itself. So if we solve for z, we should get the exact same formula. So z is right here. So that means everything else goes over to the other side. So if we solve for z, we have z is equal to, let's bring the f of x naught, y naught over to the other side. That becomes a positive. This becomes a positive as well. And the last one becomes a positive. And that's exactly the formula that they had. Okay. So this is just a quick derivation of the tangent plane. Well, I don't know if it was quick. It wasn't quick. But from a graphical point of view, where we create vectors, we see that this is one way to get to that. If you crossed it the other way, then you would have a positive fx, positive fy, and then a negative one. Okay? So we not only have the tangent plane, but we also have a normal vector that's normal to the tangent plane in this formula, or where it's positive, positive, and negative. Okay? Yeah?
So the order of where you're crossing?
It doesn't matter, because if we would have had a plus, plus, minus 1, then hopefully this would have come up to be the same equation, and it will. All right, so let me put a star here, because this wasn't really our final result, but I would consider that as something that might be important. All right, the resistor problem. What if I start it and not finish it? There are some functions that are really difficult to deal with when you're thinking about derivatives and stuff like that. And so you just have to be careful with being able to use a chain rule properly and being meticulous with your derivatives. And so this is one of them where it looks innocent enough that you're taking so your variables are R1, R2, and R3, and then your actual function is R. Now the unfortunate thing here is that they're all in the denominators. And so I hope that you don't just take the reciprocal of everything, because that's not how it's going to work. You want to find R as a function of those other resistors. And right now you have the reciprocal of that. So if you think about taking the reciprocal to get R over 1, you don't just take the reciprocals of each of those individually, because you have to find common denominators and stuff like that. So the common denominator, I think, is R1, R2, R3. So I would need to multiply this by R2 and R3, R1 and R3, R2 and R3 to get this all under R1, R2, and R3. Oh. And so if you combine this into one fraction, and then now you can take the reciprocal of both sides, then your function really is R1, R2, R3 divided by all these combinations, R2, R3 plus R1, R3 plus R1, R2. And now this makes your derivative a lot more difficult. Okay. So according to our we're going to use differentials here, right? So according to our formula, our differential dr is going to equal to the derivative of r with respect to the first variable r1, dr1, plus the derivative of r with respect to the second variable r2, dr2, plus the derivative of r with respect to the third variable dr3. Which means we have three derivatives to look for. Should I change the notation? What if I change one of the notations, or should I change all of the notations? It's the partial of r with respect to r1. It's probably easier to read this way. So the partial of r with respect to r2, the partial of r with respect to r3. Okay, so I'm going to do one derivative, and then you guys can figure out the rest. It's all the same. Should I do one derivative? Okay. Yeah, so this is one of those difficult looking derivatives. It looks like if I'm going to take the derivative of r with respect to r1, for example, I'm going to have an r1 in the numerator, an r1 in the denominator, so I'm going to have to use a quotient rule. Unless you want to, write it as this whole big mess raised to the 1 power, and then you'll have to use a product rule anyway. So I think it's the same kind of business. I'd rather use the quotient rule. Low d high. So the low is R2, R3 plus R1, R3 plus R1, R2. Times the derivative of the numerator with respect to R1. So R1 is the only variable. I have R1 times 2 times 5. I just made up numbers. The derivative of that is just 2 times 5. It's whatever's left. So R2, R3. So low d high minus high d low. So the high is R1, R2, R3 times the derivative of the denominator with respect to R1. So this is a sum of terms, and so I look for the terms with R1, and the terms that don't have the R1 disappear. So the first one's 0. The derivative of R1, R3 with respect to R1 is just R3. That's your constant. Derivative of R1, 2. So that's the numerator part of the quotient rule. Divide by R2, R3 plus R1, R3 plus R1, R2, quantities squared. That's it. You put the R1, R2, R3 values in, you're going to get a number, and then the DR1 looks like it's an error of 0.05%, so make that into a 0.005, and that's your error. And then that's the first one right here, and then you just move along to do the others. Yeah?
We should get the same answer if you actually took the reciprocal of R, but you just put the other side as all of that 1 over R1 plus 1 over R2 plus 1 over R3 to the negative 1 power. And then do chain rule. Right.
Yeah, I suppose.
We did it right then.
You gotta change that to 0.005 in the DR.
Yeah, because this is in percent.
Yeah. I'm gonna get angry.
All right, well, good luck with this. I'll take a look at that help me video and see how.
It's really, not good. Yeah. It did not help me.
All right, we got to move on. Let's move on to the next section. Which is chain rule. So, suppose I should go back to the equivalent in Calc 1, where you have y is equal to a function of u. U equals a function of x. And so if you want to find dy dx, then this is the derivative of not a product but a composition, f of g of x. And this is where you say you take the derivative of f with respect to u, and then you take the derivative of g with respect to x. This is one version of the chain rule, or sometimes we see it as f prime of g of x times g prime of x. That's probably how we know it better as, but I think the Leibniz notation will be important for us to deal with. So what we're going to do is we're going to see how the chain rule applies, or how it might look a little bit different when we're dealing with higher dimensions. And the first example for the chain rule is kind of like a special case of a chain rule. I don't know if this is a place to start, but this is where the book starts, where you take a look at a composition of a function and a curve, which should be familiar to us, I hope. If you remember, there was a problem that we did, you guys did maybe, about a cylinder intersecting something. Hyperbolic paraboloid, yeah. Yeah, well, it's kind of like a circle. In any case, if you have a function, let's do an example first without digging deep into the subject yet. You have a function, z is equal to x squared minus y squared. That's your hyperbolic paraboloid. And you're going to essentially cut it with a cylinder, a circular cylinder. And so you bring up this x of t and y of t. As something that you cut it with. What we have here is this hyperbolic paraboloid. Ooh, how do you draw that? There you go. You have a hyperbolic paraboloid, and then you have this circle down on the xy plane or up in the xy plane, depending on where it is. And you're going to see how it looks like on the surface being projected up. So this is your xy plane, and it got projected up there. Okay. So what we have here is now an equation that you can write in 3 dimensions. Where the x is just the x, the y is just the y. But what is the z? How did you get that? So you plug the x and the y into this, right? So if you were to take the derivative of this, you take the derivative with respect to t. What you have here is x prime, whatever that is, negative sign. So z prime is whatever this is. So it's 2 cosine t minus sine t minus 2 sine t cosine t. Okay? All right. So what's this got to do with chain rule? Did we do chain rule anywhere? A what? We put a function in a function. Yes, we did. We put this function into this function. Right? So let's get abstract for a minute and come back to this page. So this is your concrete example. So we're kind of doing things backward. Usually it's the abstract part and then you do an actual example. Here we're doing an actual example, and then now we're going to go abstract. So let's start with a new page saying that suppose you had a function and you have a vector function. And just so you don't let this go right away, think about the sine and cosine and then the x squared minus y squared business that we're just talking about. And then you do the composition. And the composition to get your other curve, your three-dimensional curve, remember, is that the x of t is just x of t. And we'll call this something in a few minutes. And then the y of t is just the y of t. But given that I don't have the actual, x squared minus y squared function, what if it was something else, right? How would I describe this composition here? I can describe it a few different ways, but do you have any suggestions on how to describe this third component? F of xy? F of x of t? That's one way to express that. Another way to express that is f of r of t. Now look at those two and convince yourselves that it's the same thing. Okay, so let's call this something else, S of t or something. So we have this three-dimensional curve now with the same x and y components as a two-dimensional curve, but now we're composing the third component to be projected onto that function. So if we're interested in taking the derivative, s prime of t, well, that's just x prime of t. It's easy enough to do. Y prime of t, now what? So this is where we need to think about how we did that chain rule business, or how we can apply the chain rule. So don't write this down. Yeah, times r prime of t. Okay, so this is a little bit of an issue here. It was a good guess, and that's what I wanted. And but unfortunately, there's some issue with the prime notation. Well, I've seen this before. I'm okay with that. But f is a function of two variables. So if this is my f, if z is equal to x squared minus y squared, what is z prime equal to? We have a problem, right? So that's our problem. What? So if we take the partial with respect to x and the partial with respect to y, are we combining them? How are we going to combine this? Okay, so we have. Did you put a comma between there? So the point is that this prime business doesn't work now because we have two variables. All right. So one approach, possibly, if you put a comma between them, maybe it'll work. What if we put a comma between them? fx, I'll just put fx, comma fy. Now what do we have? A what? A coordinate, right? A vector. We have two components here. Would that fit here? This times? What do you think? Dotted? Would that, is this a vector too? Well, that looks like it's a vector, right? So if we dot them, so what if we say this is fx, oh, we have to evaluate at r of t. Fy evaluated at r of t. And then now instead of just a regular multiplication, because we're dealing with vectors, let's dot that with r prime of t. Now hold on. Yeah, go ahead, you can write it. Well, let's actually figure it out. Let me switch notations on you guys and do the partial of f with respect to x, comma, the partial of f with respect to y, dotted, and we know r prime of t, right? That's x prime and y prime. Let's actually dot them. So what do we have here? We have partial of f with respect to x, dot or times? Times x prime of t. Hey, let's write x prime of t, well, I'll do that in the next step. And then this is a plus, right? Plus? Let's see if we can write this in Leibniz notation. Partial of f with respect to x times, how do you write x prime in Leibniz notation? Now, do we use partial or do we use d? We have to use d plus df dx dy dt. Now this is where you need to start writing your partials notation and the d different. Because there is a difference in math whether you use the partial versus the regular d.
That's why you can't just cancel out the dx and the partial.
That's why you can't cancel out dx and partial x, yes. Back in Calculus 1, we always say, it looks like they cancel, but don't do it. I know. You guys, I guess if I use this notation properly, I would have said dy, du, du, dx. And so people think about canceling the u's, and then you get dy dx, which is what we were looking for, right? So the reason why back then we told you not to do that, or at least I hope your math teachers told you not to do that, is because if you were to think about canceling this, then you have f df dt, df dt. You have two df dt's, and that's not correct.
The second partial there is
Supposed to be y. Thank you. So, I'd like to highlight two of them. One of them is this formula where you have Leibniz notation with the partials, and then the other one is this actual dot product that we would do. Now, let's look back at our concrete example and see if that's exactly what we had. It better be, right? Can we somehow undot this? Can we somehow get two vectors out of this that we dotted to get this result? Do you understand what I'm asking? Am I asking for too much? Yeah, like if you take the 2 cosine minus 2 cosine t, let me rewrite it so it looks a little neater. It's not much neater. If I box this and I circle this, and what do I have in my circle? I have negative 2 cosine t, comma, negative, wait, I'm sorry. The negative is with a sign here. So I have 2 cosine t, negative 2 sine t as one vector. And then I have minus sine t, cosine t is my other vector. And what's 2 cosine t? This is really 2x, where x is equal to cosine t. And negative 2y, where y was actually equal to sine t. X is cosine t, y is equal to sine t. Actually, the way our functions worked out, we only had to use one variable for each component, but really could be looking at 2 variables here. So that's really the partial of z with respect to x and the partial of z with respect to y, where we evaluated it at x naught or xy. And then this, as you can see, is a derivative of cosine and d dt of sine. So our result, in fact, did come from the chain rule, except we didn't think about it as a chain rule in higher dimension. This negative? This negative? This negative? This negative wasn't supposed to be there. That would be my bad. Because that didn't have a negative here. This negative sign is the one that was negative. Anything else we need to look at? All right, let's do another example. The thing is that it's probably just as easy to think about it the way we did it in an example versus thinking about it as a chain rule. But I think what they're trying to get at is this is going to be useful for deriving some of the other formulas that we're going to derive later on when we're dealing with composing things. And also this can easily be used in higher dimensions as well. So, in fact, let's do an example where we take it to another dimension. All right, let's see. I can make one up, or I can just look in the book for an example. Maybe like number 6 or 5 or something. 5? Probably looks like one of your homework problems, huh?
I got there, I got stuck on resistors.
All right. So here's what they want you to find. They want you to find dw dt with a straight d's. So they want you to find dw dt. Notice that w, though, is not a straight d function, right? It has x, y's, and z's, so we have to take a look at this as a partial. So according to the formula, or maybe we could approach it like this. Well, let's say, take a look at w is a function of 3 variables, x, y, and z. And x looks like it's a function of t, y looks like it's a function of t, and z looks like it's a function of t. So in the book they have this chart, or they call this a tree diagram. They have a tree diagram where they take a look at the original function, and then they go down and filter through the compositions until they figure out what the final variable is. And we see that in the final variable, you see that it's only just one variable t. So if you do that composition, w will eventually just be a function of t. That's why it's a straight d. Sometimes they look at it like this. I kind of like to think about it like this. And there's only one variable t, so it just collapses to one variable. But either way you look at this, you can see how it goes. So dw dt is going to be the partial of w with respect to x times the derivative of x with respect to t and then if we look at how many other paths get us there, the next one is going to be dw dy, but w is again a function of x, y, and z, so it's partial. dy dt, and then dw dz, dz dt. So if you look at this, this is essentially what we did in our last page, except there's another component to it. So we need to figure out our partial derivative of w with respect to x, and then with respect to y, and then with respect to z, and then we need these simpler derivatives. So these simpler derivatives are easy. I'll do that first. So 2t, y is equal to -1, and z is equal to 2. That one was easy. Now we need to figure out the w's. So dw dx. With respect to x, x is a variable. What's our derivative going to be? I want to take the derivative of w with respect to x. X is our variable. E to the y over z. Right? And I'll leave some space here because when we put it into this formula, we want to make sure we put the t in. So we're eventually going to want to set x equal to t squared, y is equal to 1 minus t, and z is equal to 1 plus 2t. This is the part where we say after we take the derivative, we're going to evaluate it at the original function. So there's no x's to put t squared in, but I have a y to put 1 minus t in. and then a z to put 1 plus 2t in. Okay? So that's my dw dx, or I should say partial of w with respect to x. Now I want the derivative of x times e to the y over z with respect to y. This time y is a variable, x is constant. So if I take the derivative of this with respect to y, it's going to be e to the yz times the derivative of yz with respect to y, which is what? 1 over z. Okay? And again, we evaluate this with x, y, and z. So wherever we see an x, we're going to put a t squared. Wherever we see a y, we're going to put 1 minus t. Wherever we see a z, we're going to put 1 plus 2t. Okay? The derivative of w with respect to z. Again, x is a constant. The derivative of e to the yz is e to the yz times the derivative of yz with respect to z. And y is a constant, right? So it stays there. And then whatever. Okay. So, your final answer. D, it's a straight, right? Straight D. dw dt is going to equal to dw dx. So e to the 1 minus t, 1 plus 2t, times dx dt. That's a derivative of t squared, right? Plus the next one, dw dy, evaluated at those points, t squared e to the 1 minus t, 1 minus, or 1 plus 2t, divided by 1 plus 2t, times dy dt, which was negative 1 plus star times 2. Okay? Sometimes people actually just put this in for those derivatives without putting the t in. But I think if you do that, you're kind of missing some stuff that this problem is looking for. So I don't know if the WebAssign allows you to just put those values in or not, or if they want to force you to put the t back. Okay, so that's chain rule. Well, that's one case of the chain rule. Yeah.
Isn't this formula pretty much the same as the differential formula, except you just divide everything by dt? Like if you factored out all the dt's.
It looks like it's the same as a differential formula. I guess, yeah, the dt is saying there's another entity that's involved here, and you're putting this as a function of t now. Okay. All right. So that's the special case where you're composing it with a bunch of functions of t. Well, it turns out that you can compose it with things that are not functions of just t, but you can compose it with functions of t and s, for example. Or you can compose it with some other things. So let me come up with another quick example abstractly. So what if you have w is equal to some function of x, y, and z, and then you have x as a function of r and theta, y is a function of r and theta, and z is a function of r and theta. So what two possible what derivatives could I possibly ask for here? dw over dr? Wait, straight or partial? Okay, so what? dw d theta, dw dr. Those are the two possible things. Now the question is a d a straight d or a partial d? Let's take a look. So w is a function of how many variables? Three variables, x, y, and z. X is a function of how many variables? 2. So the fact that it's a function of two variables means it's going to be a partial derivative.
So you have a straight D over a partial?
No, it's both partials.
Okay.
And so this is where my notation, my tree notation that goes down to just one variable, it gets a little confusing, but it'll look cool because x is a function of those two, y is a function of those two, and z is a function of those two. That's a little confusing. So the book does it like this. It'd probably be easier to read and label if you need to label it. R theta, R theta, R theta. So it repeats, but you can see the same, generally the same picture. But the point is that our variable that we're taking the derivative with respect to has two of them in the same level, r and theta. So these actually have to be partials. So whether you're looking at with respect to theta or with respect to r, it's going to be partials. So let's find a formula for one of them, dw dr. So we have to find all the paths that lead down to r. Right? So there's three paths, so I must have three things that I'm going to add up. Partial of w with respect to x, partial of x with respect to r, partial of w with respect to y, partial of y with respect to r, partial of w with respect to z, partial of z with respect to r. So that's my template formula. Now, if I had actual functions here for f and for x, y, and z, then I would just find those derivatives and then plug them in to my formula, and then I'd be set. Okay? So that's a chain rule. Kind of. Okay, we're out of time. So at the end of class tomorrow, 20 minutes before the end of class, so at 1:35, I'll stop whatever it is I'm talking about. If you want to stay to retake the last two problems or similar to those last two problems, you could stay. And if you want to submit the problems, submit them. If you want to cross out one of the problems, you can cross it out. And whatever I collect, I will grade, and it'll take the place of one or both of your last two problems in your test. Okay, it doesn't matter which got the highest score, I'm going to replace it. Okay? And of course, I'm not going to tell you what the scores are. See you guys.